Hello! Last time we made some changes to our Python prototype that we took the NumPy code and we converted it to regular for loop Python, and we arrived at this plot right here. So we have the fundamental frequency and the harmonics of the MP3 file that we're examining, and today we are thinking about improving the plot a little bit, where we can't see what notes these represent, but we would like to overlay some sort of a keyboard or something so that we can tell what is going on. So to do that, we are simply going to use another plot. So we'll define a keyboard function. It'll take the notes and it'll take some values for what the black keys and white keys should be represented as in the plot. So the mod is the modulus or modulo round ns divided by or %12. So we round the note number because this can be a floating point. We take the modulus with 12. So because there are 12 notes, there are exactly 12 notes in every octave. So mod will tell us which key of the octave it is. So num_p.zeros like ns. So here pic is the picture array that we're going to create. And then so we populate everything with the white key value, but then we just go through and selectively change the ones. So like the zeroth, these start at 0, so mod equals 0 would be the middle C, or just any C in any octave. Mod is 1 is C sharp, mod is 2 is D, mod is 3 is D sharp, and so on. Right, so then we just populate these with, take the ones that are supposed to be black keys and put the black key value to them. Suppose I misspelled one thing here. So that does the keyboard. Then what we need to do is, let's just say keyboard equals keyboard, and then we give it the notes, which is ft.notelist should do. And then here, just before, we want the keyboard to be behind the spectrum layer so that we can see the spectrum. So we're using that here, ft.notelist and then keyboard. So we can do that if we run this code. All right, so it's done. Let's go take a look at the graph. Okay, so we can see there is another curve in the back, but it doesn't match in order of magnitude. It's practically a straight line. So we need to normalize either one item or the other, but we can do that using, so freq_pal divided by freq_pal.max. So that way we are plotting this. This is all empirical anyway. There's not really a meaning to this power because we can go back and normalize things, but there is no use to it. We're just searching for peaks anyway. So we just normalize it to be the maximum value in there is 1. All right, it's done. So let's go look at this again. That is much better. So what we can see here is this peak aligns with this over here. I know it is difficult to see with the lines, but this is a G. And then, so let's see, this looks like the middle C right here. Is it 60? Let's see, the middle C is MIDI number 60. So yes, that is, this is the middle C right here, and then this is the next G. So on the violin, I was actually playing this G, which is pretty awesome. We have the first harmonic. It's kind of small, but it's definitely there. The first harmonic is at the G that I was playing on the violin. And the next harmonic is the octave higher than that, which is this G. And then the next harmonic that we can resolve from this plot is this D, which makes sense. That's the quinta away from this G. And then we have some other harmonics at different points. So isn't that awesome? We can take the spectrum of a note we're playing just by doing some frequency spectrum transformations. So here it is in full screen. You can see it. Let's do label equals So we're doing that. We named one piano keys, one signal power, and then pp.legend loc equals best. We'll tell it to position the legend at the best location. Let's run that. All right, it's done. So we can launch this, and we have a legend. It tells us that the blue is piano keys and orange is signal power, which we already knew that, but if we were to come back and look at this plot, like, I don't know, a year from now, we'll be able to tell what it's about.